see the full screen and I can hear you clearly. So please start your talk. Yeah.
Okay. So, well, first of all, let me thank the organizers for this kind invitation. And so, of course, I am happy. I cannot say I'm happy to be here because I am in my apartment and I would have rather be with all other people. But of course, I'm happy to celebrate my friends Marie-Françoise and Laurent. And okay, so we have met in Tours, and I must say that I have really very, very good memories of my staying in Tours, which was very important for me, by the way, for human and mathematical aspects. So I'm really grateful to Marie-Françoise and Laurent. They were very, very kind. And also I enjoyed our discussions so much, and all the environment I found during my stay in Tours. And of course, my collaboration with Laurent, well, I'm very happy and also proud of that, because I think we did very nice jobs. Okay, so it is a good opportunity, even if the topic of my talk is is one of my favorite equations, but it does not involve directly my collaboration with Laurent. Okay, so so the talk will be on this equation, which is often called diffusive or viscous Hamilton-Jacobi equation. But of course, you may just think at that as the perturbation of the heat operator with the first order term. And the peculiarity of this in this talk is that this first order term has a super-quadratic growth. So it will, even in part of the talk, be exactly the model case, which is the power gradient of u to the p with p bigger than 2. Here, omega is a smooth and bounded set. And so this range, this super-quadratic growth, leads us to go beyond what is called the natural growth. So we heard Lucio yesterday saying that he was scared to go beyond the natural growth, and maybe for good reasons we are going to see. But okay, I mean, in general, sons should be braver than parents. So I studied a lot this case in my works, and also to tell him, maybe in the words of Rosario, but I'm not sure Rosario is here, he would have called the dark side of this kind of equations, because it was not very much exploited until, I mean, a few years ago. So I would spend some time also to try to give an answer what is so unnatural in the super-quadratic growth, and I will anticipate a bit my answer, which is that what is unnatural is that this is a second order equation which actually behaves not completely, but at least partially like a first order equation. And this, of course, sounds very unnatural. So a short summary of my talk is that I will start by recalling some results on stationary solutions, and in particular, this gives us the opportunity to talk about this natural and a super or unnatural, say, regime. And then I will go to the case of evolution equations, and in particular to the evolution of smooth solutions, to understand how the singularities that we have observed in the stationary case, how are they happen to appear. So when and how we lose the smooth solutions, and what are the main features. So let me start with the classics. So what is natural in the natural growth? So, I mean, I like this kind of game. People who know me already maybe heard a little bit that. So what is natural in the natural growth condition? Meaning that you have perturbed your Laplacian with the first order terms which grow at most quadratically. So one natural thing is that the bounded solutions are smooth. So we learned that from classical results, I mean, in particular, Ladisevskaya, Uraltseva, but of course, all the regularity schools, Herring, Frödinger, later Di Benedetto for P-Laplacian equations. And so once the solutions are bounded, essentially they become smooth if of course the data are smooth. And then we also learned that with natural growth, we have access to very general solvability results, which means that we can relax regularity on the data, we can go to nonlinear operators, and in general, the solvability may still hold. And so there were classical results by Amann, Kasdan, Kramer, and then I would say a fundamental work by Lucio with Murat and Puel opened the way to many contributions. So it was certainly too long for me to quote, even if many of them are close friends. But of course, I couldn't stand from quoting Marie-Françoise, who gave lots of contributions in this direction. I mean, and still talking about bounded weak solutions. I mean, bounded weak solutions are unique until you have a natural growth conditions, and this is essentially a contribution by Barr and Murat. And finally, the evolution problem has global in time existence. Of course, it may happen that there is convergence to a steady state or infinite time blow up of the L infinity norm of the solution. But all those four properties hold somehow are typical of a natural growth first order terms, and we are going to see that all those properties fail as soon as we have super quadratic growth. So what happens in case of super quadratic growth? Well, let me first remind you why those equations are also called Hamilton-Jacobi, diffusive Hamilton-Jacobi. We should actually add the word Bellman equation, because this also gives us an interpretation of what we are going to observe. So this terminology goes back to the control representation of the solution as a value function. So in this case, I am describing this for the stationary, but of course a similar representation holds for the evolution problem. So in case of the stationary problem I have written here, the function u, the solution u, is the value function of a stochastic optimal control problem, meaning that assume that you have a stochastic trajectory here, starting from the point x in omega, and this diffusion process is just a Brownian motion, standard Brownian motion, perturbed with a drift term, which is meant to act like a control. So, and you want to use this control in order to minimize certain cost functional. And so the cost depends on the control. It is the evaluation along the trajectory. Of course, it depends on the trajectory xt up to the first exit time of the process from the domain. And so you see the exponent p, which appears in the equation, is the conjugate exponent of the cost functional. So, and also we know that the optimal control, the optimal drift in the dynamic programming approach is, or at least should be, in case of existence of solutions and regularity, and sufficient regularity of solutions, the optimal drift should be the gradient essentially of the solution computed along the trajectory. So it is related to the gradient of the solution. So the key point here is to observe that when p is bigger than 2, then the exponent p prime is smaller than 2. And the bigger is p, the smaller is this exponent, which means that actually the singularity are less expensive. And since we are minimizing, this means that it is easier to find singularities in the equation because it's certainly more allowed because of the cost functional to use even singular drifts, so even singular functions gradient of u. So as far as the stationary problem is concerned, I will just remind you, recall, some of you might, of course, not know, even if these results are now a little bit, 10 years old, some phenomena that we observed first in the framework of viscosity solutions with my friends Italo Capuzzo-Dolcetta and Fabiana Leoni. And of course, this was part of our analysis was in that case devoted to viscosity setting. So of course it extended to fully nonlinear operators. But then with another close friend of mine, Andrea Dallaglio, we extended also this kind of results to just distributional solutions. And of course, in this case, the results extend to divergence form operators. So what did we observe? Well, at first, so somehow we observed a list of unnatural properties which are effect of the super-quadratic Hamiltonian. So the first property is that the subsolutions of the equation are somehow regular. So they are Hilbert continuous. So the first kind of result says that an upper semi-continuous bounded viscosity solutions is Hilbert with this Hilbert exponent p minus 2 over p minus 1. And we proved that with Capuzzo-Dolcetta and Leoni. We proved that just by classical double invariable argument, of course, with a suitable comparison function. And then with Andrea Dallaglio, we proved a similar result, actually slightly more general, because we embedded this result into the class of data F in Lebesgue spaces. So if F is in Lm with m bigger than n over p, then distributional subsolutions are also Hilbert continuous with an exponent which of course tends to be p minus 2 over p minus 1 when m goes to infinity. And with Dallaglio, we showed that just by a direct application of a Morey estimate that is given from the lower order term, so from the first order term. So in both cases, this says that subsolutions cannot be too singular, and this of course is in contrast with what you would have with the case of the Laplace equation. And but there is more than that, and actually the most striking thing that we observed in both situations is that this interior Hilbert regularity actually extends up to the boundary independently of any boundary information. So actually there is an information which comes from the interior and extends up to the boundary. So it is not only actually the regularity, so in particular you see the Hilbert regularity would be necessary for boundary data, and but more than the regularity, also a size estimate is independent of boundary values. And so there is a second property which is written here, And you see here, there's a global universal bound for, in this case, for the positive part of u, because my nonlinearity is in the left side of the equation. But of course, if you switch u into minus u, you can get other results. In that case, if the nonlinearity is in the right side. So of course, it's not really important. I mean, if you write the coercive term in the left or in the right of your equation, what is important is whether you observe something for the positive or for the negative part of the solution. So in this case, though, there is a global universal bound for the positive part of u, and this bound only depends on the norm of f in Lm with m bigger than n over p, but it's again independent of the boundary information. This was related to previous results by Pierre-Louis Lyons and Jean-Michel Astrid. So this suggests that there is the Dirichlet problem cannot really be solved classically here for any boundary data. There are at least size and regularity compatibility conditions to be satisfied for boundary data. Just to give you an idea, this is a sample of what you might prove for the classical Dirichlet problem. If you want to prescribe a boundary value phi at the boundary for this equation, again, of course, p is bigger than 2, and suppose, for example, that f is continuous, then we showed with Capuzzo, Dolcetta, and Leoni that if the function phi is Hilbert continuous, which is necessary with a sufficiently small Hilbert, say, semi-norm, so there exists M0 such that if the Hilbert constant is smaller than M0, and also there is some size compatibility between the right-hand side half and the datum phi, then there is a unique viscosity solution which takes pointwise the boundary values. So this compatibility size condition is also clearly related to the control interpretation of the problem, but I'm not going to detail that. And of course, I mean, this is just a sample result in the viscosity solution setting. You might also have used a Lipschitz solution setting as it was used by Pierre-Louis Lyons in the 80s by saying that there exists a unique W1 infinity solution if and only if you may find a sub-solution Lipschitz which takes the boundary values pointwise. So this was, so in a sense, let me just make this remark for some of you who might probably have this in mind. Well, of course, you might also choose to a different setting for this equation by choosing either the setting of Lipschitz, globally Lipschitz solutions. Of course, for Lipschitz solutions, the super-quadratic growth is innocent now. Or you may use also another very interesting setting would be the W2M setting. So by requiring the maximum regularity for the solutions, but this is a little bit unclear to me which kind of general result you may show in this setting. And but in any case, if you just take F continues, well, the viscosity solution setting works very well. Of course, if you want an even more general theory, then you should be able to relax the prescription of boundary conditions, and I'm going back to this issue later on. Just one more word on this viscosity versus distributional solutions, because there is well-known example. I mean, everyone would find this example just by himself or herself, just by looking at radial solution, that precisely the Hilbert continuous function, which is the absolute value of x to the correct sharp, sharp exponent, which is p minus 2 over p minus 1. Well, this is a distributional solution of this equation. of course, up to a suitable constant C0. And this is a distributional solution, but it's not a viscosity solution. So, of course, the unique viscosity solution here is 0. And so you see U is bounded, is, of course, even Hilder continues. So this example says many things. For example, it says that the regularity for sub-solutions, the Hilder regularity was sharp, of course. But this is a minor consequence. A bigger consequence is that you see the super-quadratic growth we lose essentially that bounded solutions are smooth, and we lose that bounded solutions are unique. So in the standard, say, distributional framework. So you see that you need a selection for bounded solutions, and this is typical of first order problems. The L infinity bound does not bring enough information, as it was the case for the natural growth. So there are two first order effects that we observe here. One is that, as I say, the L infinity bound is not enough. You need a selection criterion. And the second is that you should also, you may need to relax the formulation of boundary conditions. And both these issues are very well embedded in the theory of viscosity solutions. And this is why the most general results have been later proved in the community of viscosity solutions people, in particular, by Guy and in several papers, okay? And, okay, so maybe I can go to, I was looking at a watch because I think we started maybe earlier than what was maybe scheduled. Okay, so let me now go to the evolution problem. So in the evolution problem, I will stick to the precise model when the Hamiltonian is exactly the gradient of u to the power p. This make in particular it easier to get some fine results on the behavior of solutions. So the setting, omega is still a bounded domain, smooth, and let me just consider the case of 0 boundary conditions. And P is, of course, still bigger than 2. And the initial datum is continuous with compatibility conditions. So I'm going to discuss here what is more interesting in this in the viewpoint of this talk, which is the case of reaction nonlinearity. So this is maybe why I have decided now to bring the nonlinearity to the right, which of course, as I say, you may also change by switching the sign of u, but just to fix the idea. So now my nonlinearity is on the right side and my solution is no negative. So the initial datum is no negative, the solution is no negative. So we fix the idea. This is where the nonlinearity plays against somehow the regularity of the equation. So there are, of course, many other contributions in different directions. There are contributions in the whole space. There are contributions for the absorption case of the nonlinearity, in particular Marie-Françoise with Dow, they work with the problem of initial traces, removable singularities. So those are different issues. And also there is very nice local theory in Lebesgue spaces that Bernarzi, Souple, and Weisler developed. But here, of course, I've chosen a simple situation, and the situation I've chosen is to start with classical solutions. So I want to understand what happens to classical solutions. So in particular, starting from U0, which is C1 with compatibility condition, the classical parabolic theory says that there exists a maximal I mean, a classical solution in a maximal time, T0, T star, and T star, which of course depends on the initial datum, may be finite or infinite. A few properties which we observe immediately. So U is bounded by maximum principle, and that's easy to understand. And then, but of course, this doesn't mean that you don't have blow up, because what may blow up is exactly the C1 norm of U, and this means, since the L infinity norm of U remains controlled, this means that what is possible and what is also likely to happen is that you might have what is called the gradient blow up. So the L infinity norm of the gradient of U may blow up at some moment. Now, okay, there are also several previous contributions for this specific problem, which I have written here concerning the blow up question. So some of them, I mean, I will recall also later when I will be more specific in the results that I will state. Of course, I mean, just to note as well, Philippe Souplé, who is here, is definitely probably what is most expert of this and contributed a lot. So let me start by some well-known facts that were precisely established in papers by Philippe, one in collaboration with Zhang in 2006. So this is first information we know for the gradient blow up. So the gradient blow up certainly occurs for suitably large initial data. So that's a first remark. And the second remark is very important. The gradient blow up can only occur at the boundary. So that's of course a very relevant information. It is not too difficult to show. Let me give you a quick proof. First of all, you observe that U is bounded for all times. That's maximum principle. But then what is most important, the time derivative of U is also bounded for all times. And this is a consequence of the L infinity contraction. So the L infinity contraction says that U of t plus h minus U of t in L infinity of norm is estimated from U of t0 plus h minus U of t0. But we know that for some maybe short time, but in any case, the solution was classical for some time. So it is enough to take some t0 sufficiently small so that when you divide by h and you let, say, h go to 0, well, I mean, the right-hand side is bounded if t0 is sufficiently short, and then you get a bound for the time derivative of U for all later times. There is still here a little bit of cheating from my side because, I mean, of course, I mean, I'm still, there is some piece of information which I will come back in a minute here, but until the solution exists, of course, this is true, but it will even be true in a mild sense later. Okay, so at any time t, then U of t solves this stationary equation. So the Laplacian is equal to the gradient of U to the p plus f with f which is bounded. So now you bring ut to the right-hand side and then you observe at fixed, still the solution, consider it as classical. And so you see, well, this implies that the stationary gradient bounds, which, for example, were proved by Pierre-Louis Lyons in the 85, say that the gradient of U is now bounded by only, say, the distance from the boundary. Of course, it might blow up at the boundary, but you see inside the gradient of U is locally bounded. So this is a short explanation that the gradient blow up can only occur at a boundary. Okay, so now there is a very important fact, which is continuation after blow up. So actually there exists a unique global in time viscosity solution. This was a fundamental result proved by Barr and Dalio in 2004. They showed that there exists, I repeat, a global in time, continuous everywhere, viscosity solution of the equation, satisfying, however, the boundary condition in a relaxed sense, which means that it may happen that U is not zero at the boundary, and the viscosity solution in the relaxed sense, so with relaxed boundary condition, means that if it happens at some boundary point that U is strictly positive, then U must be a subsolution at this point in viscosity sense. So somehow the equation holds wherever the boundary condition does not hold anymore. And you see this is completely compatible with the possibility that you develop, the classical solution develops gradient blow up at the boundary. And in particular, of course, the loss, say, of boundary condition necessarily implies that the gradient should have blown up, because until the gradient remains bounded, of course, the super-quadratic growth is innocent. And then we know that for Lipschitz solution, well, the boundary condition cannot be lost, I mean, as time goes by. But also this viscosity solution result tells us that there exists a natural continuation after blow up, because of course the unique classical solution coincides with the viscosity solution and is globally prolonged in that way. So this is the continuation after blow up. And let me just also add that there are also important, I mean, for people interested in regularity, this viscosity solution also remains Hölder continuous. I mean, somehow it still enjoys some Hölder regularity locally in time and space. And there are a series of results which are very interesting from the regularity theory viewpoint by Canarsa, Cardaliaguet, and also Louis Silvestre, and Stockholz, and Alexis Basser very recently. Okay, so if you don't like viscosity solutions, and I know that there are people in the audience that don't, well, you may just think of this global solution as the limit, the increasing limit of solutions of truncated problems. So you see, this is a very natural also approximation procedure. You take your power P super quadratic and then you truncate the power. It's enough that you truncate it with natural growth. Then you have a classical solution because you would have natural growth for the approximations Fn. And then you can solve with classical boundary conditions. And then there is an increasing limit Un, which converts to a function U. And this U is exactly the unique viscosity solutions. And it may happen that you may lose the boundary condition because this is an increasing limit. And it may be the case that you do have a boundary layer that brings U, I mean, to be bigger than zero at some moment. Okay, so let me stress that this loss of boundary condition, and of course, correspondingly, necessarily the gradient blow up at the boundary, so certainly occurs for large initial data. So this is a classical argument. So it's maybe nice for some of you. It's reminiscent to what happens for others, for other situations. So you multiply the equation by the first eigenfunction phi1, and you see you gain this term from the Laplacian. So phi1 is the first eigenfunction of the Laplacian with zero boundary condition. And then you try to investigate how the coercive superlinearity play a role. And assume that U is still 0 on the boundary. So that's important here. Then, not only, of course, you can dominate the projection of U on the first eigenspace. Okay, of course, this can be dominated by any power of U. Any power of U, if you do have a Poincaré inequality, here is dominated by the gradient. It is here that you use a Poincaré inequality. And then if you have chosen K conveniently small, then you can estimate this with the gradient of U to the P multiplied by the first eigenfunction up to a negative power of phi1. But phi1 is like the distance function. So if K is sufficiently small, this guy here is integrable. And so you see this guy dominates the integral of U phi1 to the power P. And therefore, the integral of ut phi1 is going to dominate the primitive somehow of its power P. So this is essentially an inequality of the type phi prime to the P phi prime, dominates the function to the P, phi to the P, provided the initial condition is sufficiently large. So, I mean, this term is going to dominate this guy here. So you see, if the projection of U0 against phi1 is sufficiently large, then with the usual argument, you would deduce that, I mean, this cannot stand for all time. And what is impossible here for all time is that U was allowed to use Poincaré inequality. Let me stress one fact here, because the last time, I mean, I have explained that there was, an expert, Fred Weisler, that I've seen here. So I welcome here, of course, Fred, and it's nice to remind this because it's last time we were together. Of course, he questioned, but is this argument really rigorous because you are supposing that the solution exists and you are also doing some, of course, integration by parts and so on. But really the argument is rigorous because we do have this global in time solution, which we somehow know very well, because this is not only somehow the unique viscosity solution, but it is the limit of increasing UN, as I said before. So we know everything of this U, and in particular, we know that this U is classical solution inside. And we also know an estimate of the gradient of U in terms of the distance to the boundary. So we know that it can blow up, but the gradient, but up to a certain extent, which makes actually those computations rigorously. Of course, you start by doing this from internal domain, and then you can reach the boundary. So in the end, you can justify this computation. So let me now say what we know for the long-time behavior. So the long-time behavior was previously studied by Benashur, Daboleanu, Akça, and then Lorenzo. And then we completed the study with Enrique Zuazua because we had some motivation in control problem. So the first information is that eventually U is going to decay like the heat equation. But what we discovered with Enrique was much more important, essentially, is that there exists some time, T0, which is proportional a bit to the size of the initial datum, such that the solution U becomes classical again after this time. So again, when I talk of U, I'm talking always of, in any case, the continuation eventually after the blow up. So the unique global solution eventually becomes again Lipschitz. It takes the boundary value again and then decays. This is why also it decays like the heat equation in the end. And so not only there is life after a blow up, but actually there is a happy ending, which means that whatever U0 is, solutions eventually become classical again and behave like the heat equation. So far, then we know that there are this kind of phenomena for this equation, which are the gradient blow up, which can certainly occurs for some initial data. Then there may be some loss of boundary condition. And then this is a completely new fact. There is for sure, if there is loss of boundary condition, there is for sure the recovery of boundary condition. And this is the first time I've seen such an example for second order equation in the dynamical case. And so, since we wanted to understand better this phenomena, well, when you want to address some difficult questions, you ask you try to like in sport, you try to buy, the best player, and then so I called Philippe, and then jointly with Philippe Souple, we developed some papers to try to analyze in a more refined way this kind of questions. And so here T star in the following is the blow up time. And let me introduce this TR, which is the regularization time. And so here the regularization means the ultimate time, so the latest time after which the solutions remains classical forever. So this is of course the analytical definition. And this is an important point because it may be, and actually precisely recently Philippe have shown that, and I will come back to that later, but it may be that the solution loses the boundary condition, then recovers, and then loses again the boundary condition. So my regularization time is really the latest time of regularization. What we showed with Philippe is that at least there are still many open questions on the blow up rate, but we showed that the minimal blow up rate is always of type 1 over p minus 2, and this is true at the blow up time. So the gradient of u of t infinity, if it blows up, it must blow up at least with this speed. And also the same rate happens in the regularization time. So the gradient of u infinity must be bigger than this power. Well, this rate is known to be optimal for time increasing solutions, or in the radial cases, there were previous results by Connor Grant and Guo and Hu, and then recently Philippe with Amala Touchy also did new contributions to the optimality of this rate under some conditions. But however, faster blow up rates can occur, and I will tell you later that. And also just a very quick hint, this is not the self-similar rate of the equation, which actually would be by scaling 1 over p minus 1. I think that Philippe is going to maybe report on that in his talk tomorrow. And also, this is related to something we showed together with Philippe for a particular case when you do have single point blow up. And actually the 1 over p minus 1, so the self-similar rate in this equations is the special blow up rate of the normal derivative. So there might be a very strong anisotropy here in the blow up rates. For the time rate, the lowest rate is 1 over p minus 2, and this happens in many times. For the normal derivative, the rate in the spatial variable is 1 over p minus 1, and the tangential blow up, which still may happen, is usually faster than the normal derivative blow up, and is, for instance, in the single point blow up, under some assumptions with Philippe, we found this rate of 2 over p minus 2. Okay, but this was just a quick parenthesis. Now let me concentrate on this issue of the loss of boundary conditions. So what we analyzed with Philippe in another paper in 2017 is that this loss of boundary condition actually may or may not occur. And this, of course, strongly depends on the initial data. So, well, first of all, the loss of boundary conditions may occur everywhere on the boundary. It's not difficult to show that. There were also results by Quas and Rodriguez in the setting of viscosity solutions. And actually what we showed is that you can essentially build initial data so that your solution blows up in any, say, relative open subset of the boundary. Okay, so here you can fix a relative open subset of the boundary, say the boundary intersection in open set, and you see you can more or less concentrate the set where the boundary condition is lost between this and this plus epsilon. So somehow by suitable sub and super solutions, you can understand, you can build examples where the boundary conditions is lost in any, say, relative open subset of the boundary. And then what is more important is that the gradient blow up may also occur without the loss of boundary condition. In this, so we observed this in one dimension with Philippe, and then more recently, Philippe extended this in his, as a consequence of his results with Patrizia Pucci and Roberta Filippucci. And so a very typical case where you can understand this is that for fixed U0, just consider the lambda U0. So you can somehow, you see, if you raise the parameter in front of your initial data, at some moment you raise a threshold lambda bar where you do have gradient blow up. And then of course, for all bigger values, you still have gradient blow up. And then what happens is that U lambda blows up if and only if lambda is bigger or equal of this value, but then it loses the boundary condition if you have strict inequality here. So somehow this U lambda bar is the threshold between global in time smooth solutions and solutions with loss of boundary condition. And then this distinguishes what we call minimal blow up solutions and no minimal ones. So minimal blow up solutions are solutions such that when you start below, you don't blow up. And if you start above, you will blow up. Okay, so then with Philippe, we gave a precise picture of what may happen in a one-dimensional case by using zero number arguments, and of course for a class of initial data. So assume a typical class of initial data is initial data which are, say, in 0, 1, they are symmetric, they grow, and they have somehow a bell shape. Okay, so imagine a typical bell shape symmetric initial data which stays at 0 at the boundary. And then what we showed is that the minimal blow up solution is exactly characterized by the fact that it does not lose the boundary condition. So in this case, there is instantaneous regularization. So you have at the blow up time, you have instantaneous later regularization. You don't lose the boundary condition. And you see you have here the blow up and also the regularization rate are faster than the minimal rate. Okay, so actually this is faster than 1 over p minus 2, but there are examples in the recent paper by Philippe with Amal at Touchy that actually they prove the blow up rate of 2 over p minus 2. And okay, so you see what happens in this case. You don't lose the boundary condition. Everything happens very, very quick. While if you have a non-minimal blow-up solution, then in this case, you have the minimal blow-up rate. So the blow-up happens, say, more slowly. Then you leaves the boundary condition. You quit 0 linearly in time. This is what this says. And then after some time, you recovers the boundary condition again linearly in time. And you see the picture of the solution. So it's interesting to observe this picture. So this is what happens whenever the solution is leaving the boundary condition. So here is U0, here is time. So the solution starts. At some point, the solution becomes singular at a boundary with this infinite gradient at a boundary, and then it relaxes the boundary condition. So it leaves zero, and for a while, the solution behaves like exactly the singularity which is described by the Hölder function, there is a mistake here because this is the behavior of the gradient of u, while u is a Hölder continuous function. So u should be x to the p minus 2 over p minus 1, and this is the behavior of the gradient. And then after a while, u goes back and finds again the boundary condition. So this kind of behavior is completely consistent and as an interpretation from the optimal control representation of the function. I didn't spend any slide on that, but just to tell you briefly, what happens is that essentially at some moment, if you start close to the boundary, sometimes it might be more convenient rather than going out of the domain, it might be more convenient to remain in the domain at the expense of a singular drift and reach the initial datum somehow. And this might be more convenient in terms of the cost rather than immediately go out of the domain, which would mean that the boundary condition is kept. Okay, I can give more explanation if needed. Okay, I'm always done. So I don't know if I'm probably not late on the original schedule, but maybe I have nearly done with the true, timetable, but this is in any case nearly the end. So just to tell you a quick hint, so the results we have showed in this precise picture I've shown here with Philippe, they are based on a zero number argument. So we use the celebrated, the famous Matano and Angenin construction of zero number property on the equation satisfied on the time derivative of u. So the key of our study is to look at the time derivative of u. The time derivative satisfies a linear equation, of course, with a singular weight, but somehow we can use the zero number property up to the blow up moment, and so for the initial data we are working with, we have somehow a dichotomy because we have that ut has only 1 0 in the first half of the domain in 0 1/2, and this just says that either the zero of ut collapses at the boundary at the moment of blow up, or it remains positive, and this distinguishes somehow whether you keep the boundary condition or you lose the boundary condition. Just to mention that there are very recent and maybe ongoing results by Philippe with Mizoguchi, and they are now they are able, okay, if I'm not wrong, that's what Philippe told me, they are able to show that the behavior can even be much more weird for other classes of initial data. So they are even able to construct solutions that have several times gradient blow up, loss and recovery of boundary condition. I hope this is not going to be the case for our present pandemic situation. And okay, so how much time do I have?
Okay, so you can talk until 3:50. So like 4 minutes left.
Okay, so I would probably use less because maybe there is time for questions. So my summary, I will just summarize a little bit. So the perturbation of Laplace equation or the heat equation with super quadratic coercive first order terms actually leads to a a new, actually hybrid model, which is second and first order at the same time, is surprisingly rich kind of equation. And we think that in the last 10 years, with several, of course, co-authors, we have enlightened this kind of phenomena, which I think were much less studied before. And you can observe from my talk either some regularity issues, like that there is a sort of competition between the coercivity given by the Hamiltonian and the possible oscillations typically due to the Laplacian. And this coercivity in the super-quadratic case gives rigidity to the equation. So this is why you have this sides or this prescription on the boundary behavior. This reminds me, and this is probably still to be exploited, something which happens in the mean curvature flow case, and we are now trying to think if there are closer similarities to this kind of equation. And then, okay, there is this fantastic issue, to my viewpoint, of the loss and recovery of boundary conditions. This is really a very new phenomena that we have tried to describe with Philippe very recently. And okay, so let me conclude by saying that, again, of course, I'm thankful for this invitation. I thank you for the attention. This is not easy to follow from the online. Happy birthday or happy celebration to Marie-Françoise and Laurent. But let me wish to you and to all of us that for the next celebration, we have recovered our boundary conditions. Because the boundary conditions, I think, are important even for mathematics. And in particular, I would say coffee breaks, dinners to share, random walks in stranger countries, personal discussions, and maybe clubs after the talks. Okay, thank you.
I think we can propose a claps.